Yeah, I'm funny, So last thing that we did, we started with the Poiseuille's equation. Sure, comes on everyone. Let's go ahead with one more question and then we'll continue with this. So let's say we have a tank here. So this tank is completely filled with the viscous fluid. This length is L, this is L. So distance between any two pipes is L. And it is observed, this liquid, right, which is there, so you actually get different heights. This height is H1, H2, H3, H4, and H5. So, and the liquid is flowing out here. You can assume the volume, liquid flow to be small. Find the relation between H1, H2, H3, H5. Just give it a try. Find the relation between H1, H2, H3, H4, H5. So why are we talking about this small liquid flow? Yeah. So if the liquid flow is small, right, then the speed of this liquid is negligible. So I can use P naught plus rho GH. Remember, we did that for velocity of efflux ka variation. Normally, if the liquid is flowing, you can't do P naught plus rho GH. But if the liquid is flowing little slowly, you can neglect that acceleration and we can use P naught plus rho GH. Find relation between H1, H2, H3, H4, H5. Okay, let's get this.
So the initial height is given.
It doesn't matter.
Okay, sir.
But we don't relation between them. We don't want the exact values.
Okay.
Again, you have to use Poiseuille's equation. So let's see. So how do we do this? So I'll just remove this lens here. So let the pressure here be P1. Let the pressure here be P2. Let the pressure be P3, P4, and P5. Right? So when you go from 5 to this point here, this is the P naught here, pressure. Now tell me one thing, the amount of liquid that is flowing through the pipe is same here, same here, same here, same here. So everywhere it is the same, right? It is the same pipe. So I can do like this. I'm using the Poiseuille's equation. Volume flow per second is given by, I'm writing between 5 and P naught. So P5 minus P naught by 8 eta. What is the length? 1, 2, 3, 4, 5. The length is 5L. 8 eta 5L by pi r power 4. Do you agree with this? So if you take the pressure between 5 and the outside point, the pressure difference is P5 minus P naught. This is the volume flow. But I can also do between 4 and 0. P4 minus P0 by resistance, this will be 8 eta 4L by pi r power 4. Is that making sense? Means if I take the pipe from 5 to 0 or 4 to 0, they should be equal, right? Because it's the same liquid that is flowing. That means I can also write P3 minus P0 by 8 eta 3L by pi r power 4. This can be also written as P2 minus P0 by 8 eta 12 by r power 4. This can be written as P1 minus P0 by 8 eta L pi r power 4. And we clearly know P5 is nothing but P naught plus rho GH. So this guy will become rho GH5 by 5, rho GH4 by 4, rho GH3 by 3, rho GH2 by 2, and rho GH1 by 1. There, that's your relation. So H1 is H2 by 2, H3 by 3, H4 by 4 is equal to H5 by 5. This is the relation between them. So actually, if you join them, you will notice something. Like this forms a pretty good straight line like this. It forms a straight line. Clear with this? So that is how they will all look like. So H1, H2, H3, they'll be in the ratio of 1 is to 2 is to 3 is to 4 is to 5. They form a straight line. What if there is no viscosity? Then what can you tell me what will happen to the heights? If the liquid is ideal fluid without viscosity, then what do you think will happen to the heights? Then they all will be same, right? If there is no viscosity, then the pressure difference is 0. So all these points will have same pressure. So the heights will be same. Yeah. Right, Shrihari. Right. Yeah. Right, Utsa. Are you clear with that? So they can play a question like that. If you have an ideal fluid and if you have a viscous fluid, then how will the heights vary? If you have an ideal fluid, then there is no pressure difference because there is no viscosity. All clear with this? And that's a little bit about Poiseuille's equation. Next thing is Stokes' law. Stokes' law is again completely experimental. So what this thing says is the viscous force on a spherical body. So this is valid only for spherical bodies. Is proportional to the radius and velocity, relative velocity of the body with respect to the surrounding. Now, this is important. So Stokes' law, we only have it for spherical bodies. You can't take any other shape. That means if you have a ball kind of thing here, if it is going with speed v, and let's say the surrounding medium is also going with speed u, the formula goes like this. F viscous is given by minus 6 pi r eta v relative. In this case, v relative is v bar minus u bar. The negative sign indicates opposition to the relative velocity. Now be careful here. The most common mistake is this. What does viscous force do? It opposes your motion. That's a blunder. Just like what does friction do? It opposes your relative motion. So for example, let's say we have the ball which is going with speed v, but let's say your surrounding fluid is actually going with 3v. So the viscous force on the ball is actually in the forward direction. It's not backward. So F viscous will be minus 6 pi r eta v minus of minus 3v. That would be 12 6 pi r eta v. The viscous force is actually acting forward. Think of like this. I'll give an analogy. See, imagine you get down from a train station or coming out from a mall. If you are walking faster than the crowd, let's say the people are walking and you're walking faster, what will the people do to you? They'll push you back, right? But imagine you're walking very slowly and the crowd is going fast. What will the crowd do to you? The crowd will push you forward. What if you're walking with the same speed as the crowd? Then there'll be no force. Is that making sense? So it's not like, when you're walking in a crowd, the force will be always backward. It depends on what is your velocity with respect to the crowd surrounding. Is that clear, everyone? So the viscous force does not depend, is not opposite to the velocity of the body. It is opposite to the relative velocity. If the liquid is going faster than the ball, the viscous force is actually forward. Clear with this? Then that's it. That is the main idea there. So this can be like a theory or a question. Let's do it like a question. We have a liquid here. Viscosity is eta. Density of the liquid is rho. You dropped a ball here, a solid sphere. Radius r and density is rho b. This is rho l. Right? Released from rest. First question. Find velocity as function of time t. Gravity is present. It's a long column, so you'll never reach the floor. It's a pretty long one. Find velocity at time t. Find v terminal. That v terminal result is important. Directly, it is a proper mains level question. That result is a mains level question. After reaching v terminal, find heat produced per second and explain the work done by the bind force. Let's get the first two. Third one we will see. Be careful. There's a bind force here. You can't ignore this. So there are three forces: mg, bind force, and viscous force. Initially, you're starting from rest. Let's get this. So this integration, right? It will look like this integration actually. Kind of. It looks like this. पाई नहीं आएगा रे वंशिका. Get the velocity as function of time t. That's a better question. Try. I'll give 2-3 minutes. It's little mathematically you have to do some work there. Let's see the free body diagram. Let's see whether you got that. mg bind force, viscous force. So this is accelerating and this is a velocity. So mg minus viscous force minus bind force is equal to mass into acceleration. Viscous force is 6 pi r eta v, right? So what is m? M is nothing but density of the body into 4 by 3 pi r cube g. What is the bind force? Rho liquid into 4 by 3 pi r cube g. So this can be written as rho body minus rho liquid 4 by 3 pi r cube g minus 6 pi r eta v is equal to mass into acceleration. So I can get the v terminal here directly. So after a long time, you reach v terminal. What is v terminal? Meaning eventually your speed becomes constant. Acceleration is 0. So if you just want to find v terminal, no need to integrate. A becomes 0. So if you put a is equal to 0, you end up with rho b minus rho l 4 by 3 pi r cube g minus 6 pi r eta. This is v terminal is equal to 0. If you solve this, so like I said, important result, you should remember this, is given by 2 by 9 r square g rho b minus rho l by eta. Should definitely mug up the result. This is a standard result when you dump a solid sphere. Right, now let's try to find as function of time t. So this was the equation I need to integrate. All clear with this page? So for convenience, what will I do? I will call this entire thing as A and I'll call this thing as B. Let's call this as P and let's call this thing as Q. And let's do one thing, bring that M also this side. M will be rho B 4 by 3 pi r cube G into acceleration. So we get acceleration, which is dv by dt, is equal to rho B minus rho L by rho B minus 6 pi r eta by rho B 4 by 3 pi r cube g into v. So this whole thing, let's call it a p, and let's call this whole thing q. You can simplify q further. So this thing becomes dv by dt is equal to p minus qv. There. Now it looks simple, but anyway we can substitute. So dv by p minus qv is equal to dt. You know how to integrate this. 0 to v, 0 to t. That would be minus 1 by q ln p minus qv. Limits will go from 0 to v is equal to t. This will be ln p minus qv minus ln p. So that will be p is equal to minus qt. Therefore, we get v is equal to p by q into 1 minus e power minus q by t. There, that's your velocity. And you can substitute p and q values there, you'll get the answer. And the p by q is actually v terminal. Have a look at the integration. Just that variables look big, but it is that same integration which we did for the Planck one. Clear with this? So these are the first two parts. Velocity as function of time t and v terminal. If they ask you to draw the graphs, I hope you remember, we get the exact same graphs what you drew here. You'll get the exact same graphs. This will be g instead of g sine theta. The graphs will exactly look the same. So I can ask the graphs also. So you can play a lot in this. Then what is he asked? After reaching V terminal, find the heat produced per second and what happens to the work done by buoyant force. That's a good thing to think. Think about it. After reaching V terminal, what happens to the heat produced and what happens to the work done by buoyant force? Think, take a minute. Just have a look at this. I'll be back in a minute. Let's see. So let's see what happens when you reach V terminal there. Listen to this thing. So after reaching V terminal, if you look at the forces here, the mg is dragging down. The viscous force is up. The bind force is up. Your acceleration has become zero and velocity has become constant. So now, if you notice here, the kinetic energy of the system has become constant. Your potential energy of the ball is decreasing because it is sinking, right? It is losing height continuously. So the question comes like this: if you are losing energy, right, and your kinetic energy is remaining constant, so what is happening here in this thing? Mg is the guy who is losing energy. Fv plus Fb. So this viscous force is like friction. So it is understood. So this is the guy who is producing heat. So viscous force is responsible for producing heat. And how much is that? Heat per second, that is energy per second, is nothing but power. So that is the power due to viscous force. And what is power ka formula? Viscous force into velocity. And viscous force will be 6 pi r eta v into v. So this will be 6 pi r eta v square. And we already know V terminal is what? 2 by 9 eta r square g rho b minus rho l. So here V terminal is proportional to r square. So this heat produced per second is proportional to r into V square, but V itself is another thing, r power 5. Okay. So the heat produced per second is proportional to r power 5 here. That means if we take two balls of r and 2r, the 2r will produce 32 times more heat. So if you have two balls of radius r and radius 2r, when they reach V terminal, this guy will have V and this guy will have 4V. This guy will produce heat H and this guy will produce heat 32H. Clear? So this is understood. So the one who is responsible for producing heat is your viscous force. But there is something else here. If mg is Fv plus Fb, chalo Fv is producing heat, what is Fb doing exactly? Making sense? All your energy is not becoming heat. All the potential energy that you lost, some part of it is becoming heat, and the remaining part is going somewhere. So if you actually look at the power due to bind force, this is a good one, right? It will be a good one discussion. They can actually ask you in advance also. The bind force will be minus Fb into V terminal. So this is going somewhere. So where is this going exactly? See, if you look at the picture, you'll understand. Because it's kind of like hidden. So initially when you take the ball, no, let's say initially the ball is here. The liquid is here. Now the height of the liquid will not change, but as the ball starts sinking, you will notice something, say. Now the ball is here. Now the ball is here. So what is happening is every time the ball sinks, right? The water in front of it here, this goes here and the ball comes down here. The water in front of it, that goes here and the ball comes here. So you can clearly see the liquid, right? It's continuously going up. So to understand better, let me show you FBD of the liquid only. If you just draw the FBD of the liquid, meaning remove the ball from there, this is how the picture will look. So you will find a cavity here. The liquid will be like this. As it sinks, the cavity will be here. Liquid will be like this. Can you see how the picture looks? Now, even though the height is not changing, did you observe something? Initially, the center mass of the liquid is here. As the cavity is going up, center mass is going up. The center mass is going up. This is the center mass of the liquid. So when the ball is sinking, the liquid is continuously rising up. Is that making sense? Right, are you? Are you able to see the picture, everyone? If you remove the ball from the situation and if you observe what happens to the liquid, can you see the space occupied by the ball is actually coming down continuously? Even though the height of the liquid is not changing, internally the center mass is going up continuously. Is that thing making sense, everyone? So the bind force, right, what it is doing, it is actually increasing the potential energy of the liquid. So center mass of the liquid is continuously going up. Therefore, potential energy of the liquid increases. So the work done by the bind force is actually going to increase. This is used to increase the potential energy of the liquid. The liquid level is not increasing, but internally the mass is going up. Used to increase potential energy of the liquid. So they can ask a question like this thing, huh? What happens to the potential energy of the system? So if you look at this thing, the center of mass of the ball plus liquid is going down. If you take the ball and the liquid together, ball is denser, goes down. So potential energy of the system is decreasing. This will be a good matrix matching kind of thing. But potential energy of the liquid is increasing. Is this clear, everyone? There, you can play around like this and see. When you say theoretical questions, these are the theoretical questions. Any doubts on this page? Please ask me if you're confused. So mg is Fv plus Fb. So gravitational is losing energy. So it is being taken by Fv and Fb, right? And Fv, what it is doing, it is producing heat. And what is Fb doing? It is taking all that energy and it is giving it to the liquid and pushing the liquid up. So if I put this in a more than one choice question, they'll ask you something like this. So when the ball is sinking in the liquid, what happens to the potential energy of the liquid? What happens to the potential energy of the ball? What happens to the potential energy of the system? You're getting it all. They're different. Potential energy of the liquid is increasing, ball is decreasing, overall system is decreasing. Any doubts on this? Clear? So this whole question, right, is like a theory plus a question and explanation, whatever. It's a pretty good thing, covers a lot. Let's see a question on this. So you need to know this formula. In case you don't remember, copy it down. You'll need this for the next one. We have two spheres. Radius is r, radius is 2r, density is 2 rho, density is 5 rho, density of the liquid is rho, viscosity is eta. Find ratio of V terminal, F viscous, heat per second. So this B and C after reaching V terminal. So after long time, find the ratio of viscous force, find the ratio of heat per second. That means they reached V terminal. I'm not asking as function of time t. Get this thing. This will be a good mains level question. Okay, get the remaining also. Near Samyak. Be careful, don't use this R power 5 wala. This R power 5 was derived under the assumption density of the ball is same. Isn't it? Rho B minus rho L is not same. That's what I said. The formula is important. It's not R power 5 here. It's messed up. I changed everything. The density of balls is not same. It's 2 rho and 5 rho. You forgot the formula. I'll write down again. See, use this formula. 2 by 9 R square by eta G rho body minus rho liquid. There. Get it. I'll give you 2 minutes. You need to, without that formula, you won't be able to handle it. Okay. Get the remaining also. That looks right. Others, try. It's just formula substitution. Right, are you? Get the remaining two. Okay. Get me the heat produced, everyone. I think most of you are getting the first part. Get me the heat. Get the heat. Get the heat. Give me the answer for the heat. The remaining all are fine. If you got the heat, then you must have got everything else right. Right, so you got it. Right, somewhere. Let's see. First thing, V terminal 2 by 9 eta R square G rho B minus rho L. So this is actually proportional to R square into rho B minus rho L. So people keep saying R square, but that is when rho body and rho liquid are same. So V1 by V2 will be R square by 2R whole square. And what is the density of the liquid? The first one was 2 rho and second is 5 rho. So this is 2 rho minus rho by 5 rho minus rho. That would be 1 by 4 into 1 by 4. So V1 by V2 is 1 by 16. The second thing, F viscous is 6 pi R eta V. I'm just taking the magnitude. So that means this is proportional to R into velocity. So F1 by F2 will be R into 2R and V1 by V2. That's 1 by 32. What is heat produced per second? Heat per second is nothing but F viscous into velocity. Right? So heat H1 by H2 will be viscous force F1 by F2 and V1 by V2. That's what I said. If you want this, you need to do the first two parts. So this is 1 by 32 and this is 1 by 16. That's 1 by 512. Check it out. Clear with this. So don't blindly mug up, that R square and R power 5. Those are the cases when the density of the body is not changing. Right, Aditi? Right, Arya? Samyak, Utsa. Who else got it? You got till the second part. Yeah, others should try. This is an easy one. You should have got it. Clear with this? Let's see one more. We have a small ball and we have a big ball connected by a string. And you immerse this whole setup inside a liquid. This radius is 2r, density is 2 rho. Rho liquid is rho, viscosity is eta, this is radius r, and this density is also 2 rho. So both the balls have same density. This is the string in the middle. So the two solid spheres are connected by a string and released into the liquid. Find a V terminal and find the tension after a long time. Solid spheres connected by a string. Now, if you think about this, just now we saw bigger the ball, more V terminal you have. So that the big ball is trying to go faster. The small one is trying to go slower. So the big one will drag the small ball with it. Find the terminal velocity of the system. Find tension after a long time. That is when you reach terminal velocity. Let's get this. This was 7. I was thinking number में कुछ तो गड़बड़ है. Is it working? So what to do? Start with a free body diagram. See, the moment you hear the word V terminal, it is understood acceleration is zero. So you just have to say net forces is zero. So how many forces are there? Two mg's, two buoyant forces, two viscous forces. Tension is internal. So take the two balls as one system and draw the FBD. So the two mg's are balanced by two viscous forces and two buoyant forces. And done, you'll get V terminal from directly from there. Mg by 4 by nr. Okay, what is m but? Samyak. M of what? Try, I'll give you a minute more. 16 Rg by 3n. Okay, let's see. So this mg will be 2 rho 4 by 3 pi 2r whole cube g. The bind force will be rho 4 by 3 pi 2r cube g. So I can actually directly subtract these two. So I'll get rho into 4 by 3 pi 2r cube g. Viscous force will be 6 pi 2r eta v. Tension is internal, so it won't matter. Again, mg will be 2 rho 4 by 3 pi r cube g. Bind force will be rho 4 by 3 pi r cube g. Viscous force will be 6 pi r eta v. So if I take this and take this, subtract them directly, I'll end up with 2 rho minus rho 4 by 3 pi 2r cube g. This also 2 rho minus rho. I'm skipping steps in calculations. You can do it on your own. R cube g. This must be equal to this viscous force plus this viscous force. That is 6 2s are 12 and 6. That would be 18 pi r eta v. There. That would be how much? That is the 8 plus 1, 9. 9 by 3, 3. That is 12. 12 pi r square g is equal to 18 pi eta v. V terminal will be 2 by 3 pi goes off r square g by eta. Check. Right, Samyak. Right, Aditi. Right, Utsav. Solve it, Narya. Simplify it. Nee, Anmita, you got tension. Okay. How do you find tension? Take any one ball. I'll take the small ball. Tension plus mg minus F by force minus F viscous must be 0. So tension must be 6 pi r eta v plus Fb minus mg will be rho into 4 by 3 pi r cube g. There, substitute that, you'll solve, you'll get the answer LBT. You could take any one ball. If you want to find the FBT, you take any one ball get FBT. Clear with this? There, it's just putting the forces and solving. There's nothing there. It's just lengthy little, but you can do it. Yeah, let's see one more. So be careful. Every time they won't ask you that's just formula only. They can play around a bit. We have a tall building. So from the top of the building, you took a small ball and you projected horizontally with speed u. And there's an air resistance. So if you see in kinematics, we ignored air resistance. The viscous force F viscous is given by minus k into v bar. K is a constant and v is the velocity of the ball. So don't worry, k is given. That means we don't need to do that 6 pi r and everything. V bar is the velocity of the ball. So just to give you the context, if the ball is going like this, at some point it will have a velocity v bar. So the viscous force is opposite to this velocity. Your gravity is present. Mg is anyway there. So there are two forces now. Mg is there and viscous force is there. First question. Find velocity as function of time t. Let's choose the downward as y-axis and the horizontal as x-axis. So I'm using down as y and this as y. Find x and y coordinate as function of time t. So basically the point of projection is your origin. I'm taking right as positive and down as positive. Find x comma y at time t. And find range. If the height of the building h tends to infinity, find range. So eventually, right, this building, this will fall on the ground somewhere. It's a tall building. It will not exceed a certain x coordinate. This ball will not keep going forever in the forward direction. At some point, it will hit the floor at some x coordinate. You'll understand. Let's get A and B. This is pure max problem. Meaning for the first 2-3 steps, right? Once you get the force, it becomes pure max. Let's see. It's a good integration. Let's see how you handle this. There, your kinematics and viscous force. Let's see how you handle this. Try 2 minutes, then I'll give you the equation part, and then I'll give you another 2 minutes to solve. mg you will get velocity vector, na? There's an I cap and a j cap. And think about this. Every time the velocity vector is changing, your viscous force ka direction is also changing, right? So mg and viscous force are not in the same direction. So how are you subtracting them directly? Think, take a minute, I'll show you. Let's see. I'll give you the equations. So let the velocity be v bar be vx I cap and vy j cap. So at any instant, so viscous force will be how much? So F viscous will be minus k vx I cap minus k vy j cap. So if you take the ball, the forces will be mg. You have k vy acting upward and you have k vx acting horizontally. That means this guy will have two accelerations. This guy will have ay and it will also have ax backward. Clear with this? So then when you write in the horizontal vertical direction, and remember initially your ui is 0, your ux is u. These are your initial limits. So in the vertical direction, we have mg minus kvy is equal to may. And you know what to do with that? You can integrate this. So this is g minus k by m vy. This will be d vy by dt. Integrate this. You will get Vy. Similarly, for x, you will take Kvx is equal to Max. So Kvx will be by M. This will be minus dVx by dt because the Ax and velocity are opposite. Integrate this thing. You'll get Vx and you'll get Vy. Now can you try? I'll give you another 2 minutes. Integral kv dt is displacement, but that is of no use, na, God. Then you'll get velocity as function of s. No, the question is find the velocity as function of time t. Are you clear with the steps? So can you solve now? Over, matlab, the physics part is done. So if you integrate 2 times, you'll get y coordinate and you'll get x coordinate. Get as function of time t ना वो छोड़ के बाकी सब कैलकुलेट किया तूने. We did something like this in old kinematics question, I guess. वो vertical projection में ना उसमें VDT becomes displacement. I know. वो 1D ना that was easy actually. यहाँ पे it'll be little messed up. Integrate. Just max question at this point. Let's see the integration. You must have got used to this integration by now. Keeps coming a lot. Minus k by Vm plus g is equal to dt. Integrate this 0 to Vy because initially Uy is 0 and 0 to t. This thing looks like Ax plus b. So in case you don't remember, I'll just write it down here. So dx plus Ax plus b ka integral is 1 by a ln Ax plus b. Get used to this integration. By now already you must have seen this 3-4 times. So a ka place में we have minus k by m. So this is minus m by k ln k by m Vy plus g. When you put Vy, you get the same thing. But when you put 0, you get a g there. So minus k Vy by m plus g by g is equal to t. So we get Vy is equal to mg by k into 1 e power minus kt by m. That's your Vy, everyone. And if you integrate this again, dy by dt, because you need to find x and y coordinate anyway, so let's finish off in one stretch. So you'll get y coordinate is equal to mg by k. That would be t. Here you have to be careful, because let me show it in the next page. We get y coordinate is equal to mg by k. This would be time minus minus m by k, again e power, I'll show you that integration also in case you forgot. E power ax dx is 1 by a e power ax. So that is 1 by minus k by m, so minus m by k, e power minus kt, limits from 0 to t. I said, why I said to be careful now, e power 0 is not 0. That is a mistake generally happens. This is mg by k, t minus minus becomes plus. When you put t, you'll get m by k e power minus kt, but when you put 0, you get minus 1. There. So y coordinate will be mg by k time minus m by k 1 e power minus kt by m. There. That's your y coordinate. Check it out, little lengthy. That's a little working for y coordinate. So if you look at here, y coordinate actually keeps going forever. The y coordinate is increasing, it never stops. Clear with this. Now, what about the x coordinate? For the x coordinate, we got kvx is equal to max. So ax will be minus dvx by dt, because here, if you see, velocity and this thing are opposite. This is a little better integration. It comes out faster. Limits will be u to ux and 0 to t. We get ux is equal to u into e power minus k by m dt. Integrate this again. We get dx is equal to e power minus k by mt dt. 0 to x and 0 to t. We get x is equal to mu by k 1 e power minus kt by m. You will notice something here. At time tending to infinity, e power minus kt by m will become 0. Your x ka value will tend to mu by k. This is your range actually. Means no matter how long you wait, your x coordinate cannot exceed this value. So if you actually draw the picture, this is how the picture would look. If you take a tall building, so there is an invisible line here. Whose distance is mu by k. So when you projected this particle from here, the y coordinate will keep increasing. You'll keep getting closer and closer to this line, but you'll never touch that line. And eventually at infinity, your vx becomes 0 and your entire velocity, right? You'll get vy becomes a terminal velocity. So if you put this is 0, mg by k. So eventually at infinity, you're just going with vy. Basically, your viscous force becomes equal to mg. So this is how the trajectory will be. So the particle will never cross the mu by k x coordinate. This is what actually happens when you throw stones from a building. The stone will not just keep going forever. At some point, it will just become straight and it will fall there. It cannot exceed a certain value. Or you can say never crosses x is equal to mu by k. So there is a limiting value there. Please have a look at the integration once. Like I said, it's more of a max question, double integration involved. Clear what we did? So the main thing was this equation, then integrated 2 times, and then this equation and integrated 2 times. You'll get x and y coordinates in the velocities. And this is how the picture would look. Yeah. Minus k. That would give you the x ka thing. But you'll not get the v by vx. Nah? That's what I'm saying. All clear with this? There, it's a good question. Like I said, but more of max oriented. There, with that, we are done with viscosity. Right? Like I said, viscosity, there are primarily 3 concepts: Newton's law of viscosity, Poiseuille's equation, which was actually derived from Newton's law of viscosity and Stokes' law. The next chapter is surface tension. We'll do it after the break. So take a break, come back in 5-6 minutes. We'll continue from here. Yeah, hands on everyone. Let's start off. The next one, surface tension. Now, the chapter can be confusing because people don't actually understand why is the surface tension, what it is coming. So we will focus on that part a bit. So once you actually understand and once you start believing surface tension exists, then it becomes easy. So the important part of this chapter is to believe surface tension exists. Right. So what is this exactly? Surface tension and everything. The first thing, let's start from the ground level. Now, when you take a liquids, right? Have those comes on. In liquids, molecules interact with each other, right? With up to a distance of, I can say, molecules interact with other molecules. Surrounding molecules up to a distance of 15 molecular diameters. Now, when you say interact, how do they interact basically? In chemistry, you must have studied van der Waals forces. Now, in case you're wondering what is van der Waals force, I'll just give a brief idea there. Think about this. If you have a nucleus and we have electrons going around, and if you have another nucleus, even though the nucleus is neutral, if you think about this nucleus is attracting this electrons because it is closer. This nucleus is attracting this electrons because it is closer. Even though the nucleus and nucleus are repelling each other, there is also an attraction between this nucleus and this electrons. And understand, sometimes the electrons are closer, sometimes the electrons are farther. So this will result in some kind of an attraction between the molecules. So basically, that is the meaning of that. So these interaction forces, right, is what we call as van der Waals forces. So that much idea you should have. Even though we say the molecule is neutral, in reality, the charge distribution is not really uniform. The electrons are moving around. And now, why only 15 molecular diameters, not more or not less? So again, this thing is mostly kind of an assumption, and kind of like an error thing. If the force between the first two molecules is 100, so then I think they must have taken a molecule where the force becomes like 1%. So after that, you're ignoring. There is a force between 20th molecule also, but it is small compared to this, so we ignore it. So what do you mean by 15 molecular diameters? So if you have one molecule here, from here, if you draw a circle of 15 molecular diameters, it will interact with everyone in this circle or sphere. Clear with this? Think of like this, huh? You go to a party, right? And there's a little crowd there and everything. And if you shout, so up to 15 people in every direction can hear your voice. The 16th guy can't hear your voice. So basically you can't call him, so you can't interact with him. You can think of like that. So that is your main idea. So we start with this one thing, that every molecule will interact with another molecule up to 15 molecular distances. So now when you go into a liquid, you will notice there are actually three different force profiles. So if you take a liquid in a container, there are three different force profiles we have here. First thing, if you look at the molecule inside the liquid, this molecule is pulled by the force in every direction because it is interacting with 15 molecular diameters in every direction. So this guy will experience F net is 0. That means the molecule which is inside the liquid will have net force 0. There is a molecule on the surface will get pulled only inside, right? But there is no upward force because outside it is all air. So there is a net downward force. So molecules on the surface will experience a net downward force. The molecule inside the liquid will not experience any force. Whereas the molecule on the edge will experience the force due to the liquid, but they also experience force due to the solid. These are called adhesive forces. Adhesive forces are forces between unlike molecules. So it is an interaction between liquid and the solid. कभी फेविकॉल का बॉक्स देखा? It will be written there फेविकॉल adhesive करके. Adhesives are those substances where you can stick two different materials. You can stick wood to the wall, wood to metal. Getting it? These are all adhesives. Force between unlike molecules. Cohesive meaning force between like molecules. So that if you see actually there are three different force profiles here. The one inside will have zero force. The one on the surface will have a downward force. The one on the edge will have a different kind of force profile. We'll talk about that. So this 15 molecular distance, right, which I was talking about, this is called sphere of influence. So this radius is 15 molecular diameters. This is called a sphere of influence. Like I said, you will interact with everyone in this sphere. So coming back to this thing. So in the liquid, we have three different force profiles. Just give me a minute, right? Someone is knocking. That's it. So first thing, the molecules inside the liquid have zero force. So these things, they do nothing. So we're not interested in them. The molecules on the surface, they create something. So we are interested in that. We'll study that first. That's what will lead to surface tension. And the molecules on the edge, they interact with the solid and liquid. This thing will lead to something called capillary action. We will see that also later on. So we are mostly interested in the second and the third one. This is the first thing you need to understand what is happening at a molecular level. Is this clear, everyone? So every molecule will interact with every other molecule due to van der Waals forces. But you cannot interact forever for infinity. So there is a limit. We have taken that limit to be 15 molecular distances, right? This was because of van der Waals forces. So if you take a molecule inside the liquid, so the net force will be zero. But if you take a molecule on the surface, there'll be a net downward force. And the molecules on the edge will have two forces, solid and the liquid. We'll talk about it later on. Now, if you try to see the molecule surface, you will notice the molecules inside, right, are completely random because net force is zero. They're doing all random stuff. They're just moving everywhere with nothing. But if you look at the molecules on the surface, now something happens. Because there's a net downward force, these things become tightly packed. They kind of create something like a barrier. So the molecules on the surface experience a net downward force and they become tightly packed there. Right? And the molecules inside, right, are they randomly moving because F net is zero. Because the F net is zero, they can just move wherever they want. So think of like this, huh? Imagine you're going to a rock show or a music concert, right? So let's say the concert is happening here. So this is the stage, concert is happening here, and there is a crowd. Now, let's say when you want to go front, what will happen? Now, tell me one thing. The people in the first line, right? Everyone will be there at the barricade, isn't it? These people must have come in the beginning. They're occupying that space so that they can get a better view and everything. So this will happen almost for 2 to 3 lines, right? People are just completely jam packed here. But if you look at the crowd here, people are just randomly placed here. So now, if you want to get through them, can't you just push through these people and can't you just go ahead? They won't do anything, right? They will let you go also, right? But the moment you try to push through the first 2 lines, what do you think will happen? They'll say like, "Are you mad or what? We came here in the morning and we're waiting in the line. You just want to come in the front." They'll start fighting with you, isn't it? The people on the first 2 lines, they get a better view. They won't let you in that easily. They will oppose you if you try to push through. But whereas the people on the other side, they really don't care if you're just trying to go inside because they're just randomly placed. So something similar happens here. These molecules on this thing, they become like a tightly packed, right? Due to the net downward force, so they start behaving like a membrane. So if you try to push these molecules, let's say if you put your finger here, and if you try to push them, the molecules will try to fight back. Getting it? So they kind of act like a membrane there. So if you actually see, right, at a molecular level, this is how it looks. Think about it. So these molecules are like this. Now, when I say like this, actually they're having a small bond here. Think of like this. People are standing in a line with their hands holding. Let's say you and your friend are holding hands like this. So human chain, people have formed a human chain like this. That is how the molecules behave. So if you want to push through these people, what will happen? They're going to push you back, right? So because of this, the surface will actually start behaving like a stretched membrane. So think of the molecules on the surface like people who are catching their hands and standing in a line. And if you try to push through them, they're going to push you back. Surface of the liquid behaves like a stretched membrane. Yeah, surface tension can hurt you. Why can't it hurt you? So try this thing. Next time, go to the swimming pool, take your hand and try to beat the water surface with palm open and see what happens. If you actually fall from a 10th floor building and hit the water surface, you won't survive. Your face will get fractured if you fall flat. That's why when people dive, what they do? First of all, they throw a stone into the water, they break the surface tension, and then they jump like this with the legs down. No one jumps like this into the pool. Only Bollywood heroes will do this. If you fall like that, from at least 7 or 8 floors, you will hit the floor as if you are hitting a concrete floor. So if you think, right, you can jump into the pool and you'll survive from 10th floor, nice try. So you should first of all fall like this. So this way you are actually piercing that surface and you're entering. You still have some chances, but if you fall flat, you're gone. Nah, next time I'm telling you, when you go to a pool or something, take your hand, stretch your hand like this, and try to beat the water on the surface. It hurts. Your hand will just not go inside. So because of this tightly packed molecules on the surface, right, they act like a stretched membrane. This property is called surface tension. You might think like this, sir, if they're just forming bonds, why is the thing pushing out? Just think of like this. Let's say you and I are standing there we are holding hands and you're standing, you and your friend. Now, if I try to come from the middle and try to push you, what are you going to do? Look at your hand. Your hand is applying tension this way. Your hand is applying tension this way. Theta, theta. The resultant force will be this way, isn't it? You're not pushing actually away. You're actually pulling at the angle, but the resultant of the two molecules will be pushing out. Is that making sense? So surface tension is not outside. So just to give you an idea, this is how it would actually look. Like I said, first of all, you really have to believe surface tension exists. Once you actually believe, it starts becoming easy. Look at this. That's a mosquito sitting on a water surface. Can you see how this water surface is bending here? So if you're very lightweight, right, the water can actually sustain your weight. Humans can't do that, but these mosquitoes and everything are just sitting there. Did you ever observe this thing? This BMC comes and sprays that, white color smoke everywhere, and they spray some kind of liquid on the surface. And they say like it is to kill the mosquitoes and all. And we think like, yeah, these BMC people are must have, putting some super chemical and all. Bullshit, it is just kerosene. So the idea is this: when you put kerosene on the water, the surface tension decreases. So when the mosquito lands, it cannot support the weight. A mosquito sinks and dies. You're actually killing mosquitoes by drowning them. So they go to the areas where the water is stagnant. They just spray some kerosene kind of thing, right? And the whole surface tension breaks down. So any insect that sits on the water will sink. You're actually killing mosquitoes by drowning, not by using some super chemical which they invented. Clear with that. So let me show you how to do. So what happens? What if humans want to run on the water? Now we can't exactly run on the water, but we can try something like that. This is how it would look. Okay. Young Costa Rican basilisk lizard. This is called Jesus Christ lizard. That is the actual name of the lizard. Getting it? So basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young female. So there is a lizard there. It has its areas. Okay. So we'll see what happens. So now that is our hero there with the mouth open. Cute. There, that is our villain, a snake. So snake is trying to eat our lizard.
This predatory reptile will help reveal the secret as it stalks the young basilisk.
Look at this thing, how it runs. It runs on the water. Can you see how it is running? Nice motion, na? The legs and all. It runs a little weird. Bexy.
The basilisk.
There's a lot of physics involved here. Huh? First of all, right, if you see this lizard, the feet, right, are not like normal feet, they're webbed feet. That means there is a web between the fingers, so you can actually get more surface area in contact, right? And when this is running, did you observe something here? Look at the tail there. The tail is acting backward. Now just try to understand. If the lizard stands on two legs, won't it fall down? The weight of the lizard, the weight of the head of the lizard will make you fall down to the left side. So the tail at the back is actually used like a counterweight. It's like a seesaw. So when it is running with the two legs, the tail is at the back. It is actually balancing the torque about the two legs using the tail and the head, right? And it is actually using the water surface tension to run on the water. Now it can't run slow. It has to run a little fast.
Is called the
That is running
The
cute.
basilisk is called the Jesus Christ lizard because it can walk, well, maybe run on water.
It runs really fast, Tracy.
Its hind legs, and the tail becomes a counterweight.
Can you see how fast it ran? So that is how it can escape snakes and survive.
Did it really want to eat the lizard? Or
so he's like, we don't know what the snake is thinking. Now that is how a snake can go on a water, but what if humans want to do? Now we can't do that on the water. We have to change the liquid.
Is that non-nuclear?
Can you see that? Can you see when that girl is running? Can you see how that surface is bending there? So this thing, right, is actually they take cornstarch and water. Cornstarch, matlab, remember they make that bhajia, right? So that bhajia thing, right? So that powder cornstarch and water, they put it in 1:2 ratio. Means for every 1 liter of water, you put 2 liters or 2 kgs of cornstarch, and you mix it thoroughly, so you get a pretty viscous thick liquid like this. So it has enough surface tension, it can balance your weight. And there you can do all these kind of stunts. There, they mix up the cornstarch with water. So there it becomes pretty viscous there. There, that's a like all that jelly kind of thing. Now the thing is that you have to keep moving. Huh? The moment you stop moving, you'll start sinking. You can clearly see the surface bending there. This is what I was saying, little. The entire surface acts like a membrane. If you stop, you'll sink like this. But luckily, you won't die because of drowning, because the density is more than you, you'll always float. This guy is crazy. So the idea is this: when you are hitting it suddenly, right, it exerts a force on your surface, you can balance the weight. If you stop, this is what happens. And send this video in the group, you can check it out. There. Someone is even trying to cycle on top of it. It got inside. People are dancing. There, surface tension exists. It's not our imagination. But this guy is doing flips also. There, it works like that. So that is your surface tension. Arya.
Sir, in the video they mentioned something like
One second,
non-Newtonian.
bolo.
So what is non-Newtonian?
That thing which does not obey, does not flow like that. Eta A dV by dz I na. Newton's law of viscosity thing.
हाँ हाँ, उसका विस्कोसिटी
Uh,
वैसे नहीं रहता.
it doesn't obey that.
ओके.
Clear with this? So everyone is getting now what is happening with the surface. So the reason why you're getting surface tension is because the molecules on the surface are tightly packed. And because of that tightly packing, right, they're forming like a membrane there, like they're forming a boundary there. They're not letting anyone push through. They'll oppose you, they'll fight back with you. So this property is called surface tension, and that is how these mosquitoes can actually walk on the surface. And if you use a very thick liquid, even you can start running, or you can go to Jesus Christ lizard. But name is highlight for that lizard, right? Now, when you keep saying surface tension, so let's define what is the surface in the first place. What is the surface then exactly? So surface is simply a thickness of 15 molecular diameters. So that sphere of influence, right? So we take the 15 molecular diameters. The thickness of 15 molecular diameters at the interface is called the surface. So if you take a liquid drop, and if you take a soap bubble, and you have soap solution here. So in a liquid drop, right, you have a liquid inside, you have air outside. So basically this is one surface. Like I said, the interface between two mediums is called a surface. So a liquid drop has one surface. But if you look at the soap bubble, we have air inside, we have soap solution here, we have again air inside. So there is one and there is two. There are two surfaces. So be careful with that. Whenever you handle soap films and surfaces, right, we always have two surfaces. And the thickness of a soap film, right, is generally around 2 to 3 lakh molecular diameters. So compared to 15, it is pretty thick. 'Around 2 to 3 lakh molecular diameters. So for a soap film, we'll have two surfaces, and think about it, Nare Aditi, the moment you hit it, right, the molecules will start getting compressed, isn't it? For a moment, there's no space for them to go inside, no, suddenly. Inside it is already packed. But think of the same thing, right? See, imagine if the people are standing in the line, if you just try to force them, they will oppose you. But if you just stand there and gently try to push through, you can eventually pass through, right? So think of like that. So when you hit that suddenly, right, the forces will be large enough to oppose you. It feels like a surface. But if you gently put your finger and push through, then you can just enter. Clear with this thing, everyone? Two surfaces. So all soap films will have two surfaces. So a liquid drop will have one surface. This is important. Now, great. So we all understood now that there is something called a surface tension force and everything. But how much is this exactly? Now, if you take a surface, listen to this carefully. This is another little thing. So this is your membrane kind of thing, the surface. Now, A, B, C, D, E, and F. So if you imagine an imaginary line between C and D, we will observe the right side of this is pulling with a force F. So how to imagine this? Look into my screen. Huh? If you look into my screen, think of like this. Now, if this thing which I have is my surface here, right? And there's so this thing, the paper which I have is my surface here. And imagine if I draw a line here. Can you see this thing? I'm drawing a line there. So if I draw a line in the middle, right? So there's a line there. Now imagine if I'm pulling this with both the sides. Isn't that what the surface is trying to do? It is acting like a membrane. So if I'm trying to pull on both the sides, now if I ask you this question, on this line, what is the force due to this side? Which side? It is pulling this way, right? So when I'm pulling this way, it is pulling this way. What is the force on this line due to this surface? It is pulling this way. So basically on this line, there is a force here and there's a force here. So there's a force acting on both the sides. Getting it? Now, because it is an equilibrium, so this is the force due to ABCD surface. This is the force due to the CDEF surface. Getting it? So that imaginary line is pulled by two forces here. So this is how it is given. So the surface tension force depends on the length of the surface, because think about it, more the length, you have more molecules. More molecules, you have more force. So surface tension force is parallel to the surface. So that is the first thing. The surface tension force is not pushing you out. It is parallel to the surface and perpendicular to the line. Meaning, again, look at the thing, okay? If you look into my screen again, if I ask you how is the force on this black line? On this black line, if you observe, how is the force? The force is this way, right? The force is this way. And how is this force? This force is parallel to the surface, right? And this force is perpendicular to the line, no? So when I'm pulling this way, the force is acting parallel to the surface and perpendicular to the line. Clear. Then you might ask, like, so then why is it pushing? Now think of like this. So if this is the thing, for some reason, if someone comes and tries to push through, what will happen to this thing? This will bend like this, isn't it? Won't the surface become like this? It was flat like this. Now if someone comes from the top and pushes this plate, the surface will start bending like this. Now if the surface bends like this, now how is the force? Now if the surface is bending like this, so one force is acting this way up and one force is acting this way up. The resultant of these two forces will be outward. Is that making sense? Surface tension force is not pushing you out. Surface tension force is trying to act along the surface. But because you came and you messed up the surface suddenly became bent. And because it became bent, the force became a vertical component came suddenly. And if you think about this, isn't that what happens when two people are standing in a line? Let's say you and your friend are catching hands like this. So initially the force was straight. Now, if I come from somewhere and if I start pushing you here, what will happen to your hands? Your hands will become like this because I'm pushing you. So now your two hands will apply force like this and force like this, and the resultant force will push you out. I hope that is making sense. So whenever you want to visualize about surface tension, think of two people catching hands. That's a pretty good analogy there. And you'll understand how is the force acting. The force is acting along the hand and perpendicular to that line. So these are the two important things. The force is parallel to the surface and perpendicular to the line. So that means if you take not only this thing, if you take any random line, and if you look at the force here, the force will act perpendicular to this line and parallel to the surface. Since because both the sides, the lengths are equal, they will cancel out. So that's the reason line does not move. So this force is proportional to the length of the line. The proportionality constant F is equal to SL. So S is the surface tension, which is force per unit length. So that S depends on the nature of the material and temperature. If you increase the temperature, the molecules on the surface will start becoming more random, so they will not fight back properly. The surface tension drops. We will talk about that also. Clear with this? So, let me ask you something. Listen to this carefully. Imagine we have a plate like this, and let's say you keep a rod in the middle. And let's say there's a soap film here, and there's a soap film here. Now, just now we saw force is S into L. So this film is applying force F. This film is also applying force F. And understand, it does not depend on the area of the film. It depends only on the length. Both the forces are equal. Agreed? Now, somehow, for some reason, if I pop this soap bubble, what do you think will happen? Now, there's a force on the right side. So this rod will start moving to the right, isn't it? Make sense? And similarly, that is one. And let me explain the other one also. So let me show you how does it work. Now listen, see this carefully. Yeah, this is important. This is the final thing. Matlab, this is the thing which will make clear that the force actually exists. And we have pretty good music also. There is this.
Even further by surrounding the soap molecule head. This kills the surface tension, close onto the bubble, nature of surface tension.
Look at this
We can
thing.
show.
So there, this guy made a rectangular frame like I showed you, and in the middle there's a movable wire. So everyone listen to this, see this thing carefully.
The energetic nature of surface tension. The rectangle made out of copper, one side bar multiple.
So there's it. You have a rectangular frame, and in the middle you can see that copper wire that can be moved. Okay, now he's putting this in a soap solution. Now when you put it and take it out, there can you see now there are two soap films. There's one soap film on the right and there's one soap film on the left. And since both the lengths are equal, they're pulling that copper ka thing in the middle with equal force. Now see what happens if you remove one of them. Did you see how did it move? Look at this thing. So here mg sin theta is pulling it down, so it is coming. But if you make it flat, it goes back. See that again. You immerse that in the liquid. You got two soap films. You remove the thing in the left one. Did you see how did it move on the right side? See that again, how it moves. There. I hope that is convincing, right, sir? Soap film actually pulls you. That is one. There is one more thing. Look at this thing.
I'm going to show you a really cool experiment with water and ground black pepper.
You can do this at home.
By taking a plate, I like to use a wok one like this and pour on some water. Then take your pepper and sprinkle a bit all over the water like this.
So that is
You
pepper.
can see the pepper sits on the surface of the water, and if you dip your fingertip in, nothing really happens.
So if you just put your finger there, nothing happens.
You might get some pepper stuck to your finger, but that's about it. Next, take some washing up liquid.
So you can take that Vim hota hai na, that soap solution, washing, this dishwasher.
And wipe a tiny amount
So
on
take
the
a
end of
little
your
thing.
finger, like this.
Now see what
Then
happens.
try dipping your finger into the water again. As you can see, the pepper seems to magically shoot away from your finger. So here's what's happening. The pepper sits on the water because of the high water.
So what is happening there? So how do you explain the second thing? The second thing, what is happening, So when you have the water there and when he kept the pepper everywhere, so if you just look at any one pepper ka thing, the surface tension force is pulling it in equal directions in all directions, agreed? The net force is zero. But the moment you added soap solution here, the surface tension decreases. We will see why it decreases. So moment the surface tension decreases here, this is what happens. So on one side, the surface tension decreases, but the other side, the surface tension is still more. So suddenly the pepper molecules will start going away from here. So it gives you a feeling as if they got repelled, but it is actually due to the surface tension. You can actually try this at home. You know that camphor which we have, the white wala, kapur? If you take that and put it in the water, observe it, it dances. It doesn't stay at one place. It keeps dancing everywhere on the surface. Because every time the kapur melts, it will change the surface tension. It will go in the opposite direction. If it melts here, it will go in this direction. So the kapur will, if you see that, it feels as if it is dancing on the water surface. Clear with this thing. So there is a force called S into L which acts on the surface. So that's what we saw in that frame there. So if I take few examples. So if you bend the surface, this is what happens to the surface here. And if you keep a rod or something here, it's like the thing which I showed you. What happens if you bend the surface? So here the surface force will be like this. It will be along the surface and perpendicular to the rod. And if you look at the same thing in the side view, it looks like this. The surface got curved. So we have one force here and we have one force here. The forces are like this. And if this is theta and this is theta, and if this rod or something has weight mg, then we get 2f cos theta is mg. And then this f is given by S into L. What happens if we take a soap film? Now be careful, a soap film will have two surfaces, remember? Just now we discussed it has two surfaces. So whenever you take soap film, you have to multiply everything by 2 into 2. So there is one surface on the top. So here is one surface here, S into L, and there is one surface here, S into L. So the soap film will have two forces, the upper surface and the lower surface. That means if you take a rectangular frame like this, and if you put a rod like this, and if you tie a weight M here, and if this is the soap film here, surface tension is. So when you draw the FBD of this rod, there will be two surface tension forces. One surface tension is because of the back ka film SL. So this is due to the back side. Think of like this: when you take a page, there's a front side and the back side, and there is one force on the front. This is due to the front side. So a soap film will always give two forces. And the rod ka weight mg, and equilibrium will say 2SL is equal to mg. Is that making sense, everyone? Right? And you can keep giving more examples. Let me give you a few more. Suppose if you put a plate on water surface or liquid surface, so disc on a liquid surface, and if you try to pull this disc, gently, little, not too much, you will notice the liquid actually rises. The liquid actually rises like this. You know how it's like your shirt collar button. If you catch your shirt collar button and pull, how does your shirt rise? So basically, this entire force here, the surface tension force will be like this, which will be circumference 2 pi r into s. That will be the surface tension force. The liquid will pull you up. And if you have a force F upward and the plate ka weight is mg, so you require mg plus 2 pi rs to pull the plate out. So if you have a plate on a water surface and if you're trying to pull it out, it is not only mg, but it is also the surface tension which won't let you go out. You can make this even better. If you have a liquid surface and we keep a disk like this, a disk with a cavity. This is R1 and this is R2. Now, if you try to pull this thing, this is how the liquid surface will look. This entire thing will be filled with liquid. So we get one surface tension force on this side. So every time you touch, you get one surface tension force. 2 pi R1s, and you get one surface tension force here. 2 pi R2s, then your own weight mg. So someone needs to apply F to balance that. So there, basically, every time you put something on a water surface and if you try to pull it out, it is just not mg. The surface tension will start sticking to the plate, right? And it will try to oppose you from going out. Clear with this? Right? So that's a little bit of our introduction about surface tension. So we just saw that F is equal to SL. So the main thing is you should understand and accept like, oh, there is something called surface tension. Once you're comfortable with that, and once you know how the force is acting, the problems will be quite easy. It will be like mechanics again. But what I found always is people get the equations, people write the forces, but they're really not convinced that surface tension force exists and how does it act. So that's what we tried to do today. So please make sure to go through this again. So next class when we catch up, we'll continue with this, right? We will talk about little more about properties and we'll see more numericals on this in the next class. Again, quite a small chapter. We will wrap it up in 2 classes. And then after that, we'll start off with elasticity and then we'll go for heat and thermo. Okay, with that, we'll wrap up further. And do remember, there's a test online till tomorrow night, so make sure to give. So any doubts, anything else, please stay back and ask. Also free to